Okay, so larger studies will detect sort of effects with a higher probability than smaller studies. We kind of know that, but it's important to think about. However, there are other things as well, in that if we're trying to spot a big difference, we are more likely to spot that than a small difference. If a new therapy changes survival by 1 year, we're more likely to detect that in a study of a given size than if it increases survival by 1 month. Okay, so we need to think about effect size. And then also, there's the background sort of fog, the variation that sort of makes the niche statistics is this thing called individual variation. So the more outcomes vary between individual subjects and patients, the lower the power of our study. So we want to reduce individual variation to increase the power of a study. So there are ways of doing that. So one thing we do, in one sense, what you can do is you can go into the laboratory, you can use kind of a clonal strain of mice, which weren't very much at all, so you detect drug differences. But we're working clinically, we work in the real world. So what we can do is we can standardise treatments, we can sort of correct for baselines, we can do things to reduce the background variation so we can increase the chances of spotting effects of interest. Okay. Often what we need to do is we either need to decide sort of what sample size we want to get a certain power, a certain chance of detecting an interesting effect, or we'll look at the sample size we can afford and report what the power is. Either way is quite reasonable. So if you've got if it's easy to gather patients and subjects for a study, it's reasonable to work out how many you want to get, say, an 80% chance of spotting an interesting effect if it's there, and then you look at your 100 patients each arm of your study. If you can only afford to look at sort of 47 patients in each arm of the study, you work out what power you're going to get with that, what's the chance of finding an interesting effect if it's there, and then you decide if that power means it's worth doing the study. So either is a reasonable approach. The key thing is to think about these things. It's terrible to sort of, it's not terrible, it's what would be sort of silly would be embark on a study with no idea how likely it is to detect effects that you're interested in finding. The actual technicalities of doing sample size calculations are down, I suppose, to sort of, it depends on your study design, it depends on the statistics you're going to use, and there's lots and lots of software that will do this, both online calculators and sort of statistical tools. It's something to, if you always come back to this, read the literature, look at what other people have done, how they calculated the power, talk to statisticians, talk to knowledgeable colleagues, and that will sort of help you do the calculation. A couple of questions that we sometimes get with sample size and power calculations is, what effect size should I use? Well, strictly speaking, probably the best sort of effect size to use is, what effect size would you want your study not to have you miss? What difference in blood pressure before and after treatment, what survival time difference between the treated and untreated group would you not want to miss? That's I think a clinical judgment, but also informed to an extent by the literature as well, and sort of that informed that clinical judgment. The other thing that's hard to know is, what's the individual variation to put in my sample size calculation? And there you can look at estimates from other studies, use pilots and the like to try and see what the background variation in people's survival, in blood pressure or whatever are, to put that into your sort of calculation for sample size. So sort of that's just a sort of brief sort of overview of the sort of sample size power calculation stuff. But again, read literature and sort of also talk to statisticians before you decide what size study you want to do. Does that make sense? Any questions about that? If you sort of pop them up, I just click on to the next slide. Just have a quick sip of my tea. Right, okay, so the next lump of stuff in my sort of workflow is, clearly you're going to do the study, and there's a whole lot of stuff which is sort of beyond sort of how you sort of recruit sort of patients, recruit subjects, dig through secondary literature, sort of run stuff in labs or whatever, okay. But there are some general things that are important to look at, and that's the sort of notion of data collection, extraction, and management. So it's going to very much depend on your project and sort of how you sort of collect and organise your data. But the key general points I would make are, First of all, it needs to be sort of secure and resilient, okay? And these are quite boring things, but they're really important things. So secure basically means that you'll be collecting data which might be about patients, it might be about some individuals, there might be personal data there. So you'll have responsibility to that, and that will be tied up with your ethical consent, but you need to make sure that that data doesn't leak from you and your project team to the wider world, okay? And that's using things like encryption, password protection, not carrying data around on flash drives, not using unsecured laptops, not leaving out bits of paper, okay? And how that will be project specific, but you need to sort of have addressed that sort of point. And that also will probably need writing in grant applications and also in project write-up. Kind of somewhat sort of kind of similar, but also opposite that is the issue of resilience as well. You want to make sure you don't lose the data, not lose it as in having someone else get the data, but you don't want the data to disappear. And that's why these two things fight against each other a bit. In that one way of dealing with resilience is to keep lots of copies of your data, keep it on USB drives, lots of laptops and computers and things, but then that becomes less secure. So you need to think about a way of making sure your data is kept securely, but is also resilient, that you won't lose it. A further point with resilience as well is as you go along with a project, you will collect data and you might be recruiting sort of patients or subjects and adding to it. Think carefully about version control and sort of duplication. You don't want to have multiple spreadsheets which maybe contain different versions of data where things have been amended. Think sort of carefully about sort of how you organize things so you have a golden sort of copy which is backed up and secure. And so it's one to get into chat. I'm very much into talking to other people and sort of having people sort of say, well, what would happen if this, what would happen if that. I work with teams that do a lot of work in the field in sub-Saharan Africa, and there it's a big challenge because of things like we can't immediately back up the internet. So we're taking photos of paper data entry forms, and then we're shredding the forms once we've got the data electronically entered. So we sort of have to think quite carefully about how we sort of manage these things. And that all has to happen within your ethical consents and what's practical. If you read one sort of reference on how to organise your data with a relatively simple project, the sort of project where you would store the data in a spreadsheet, I would strongly recommend this paper by Carl Broman and Kara Wu. It's very nicely written, it's very kind of clear, and it just goes through a very methodical approach to storing data in spreadsheets and avoiding lots of problems. And if everyone I ever worked with read this, it would probably save me 20% on the average project, because for two reasons. One, if you organise your data as per this, it's very easy to get into stats software. And secondly, the actual act of following that paper, it's an open access paper, following that paper and organising data in that way will make you think clearly about what you're recording. Okay. Right. So I think probably some of this. Yeah. So back up your data. Do not lose your data. Make sure you keep an original copy. So if you edit your data and change your data after it's collected, record those as edits and changes, so you can always go back to this golden copy. Create a data dictionary, and the Broman Wu paper talks about that. So make sure you're clear what columns mean. That will matter with working with collaborators and your statistician. You don't want your statistician or your colleagues to guess what a column means. More of that on the next slide, but make sure you have, as a separate sheet, maybe on a spreadsheet or a separate document, something describing clearly what things mean. So what unit something is measured in, sort of what missing value codes mean, sort of just get that sort of rock solid. So you have so someone given your data sheet and that data dictionary knows exactly kind of what it means. That will sort of save a world of pain later on. And also be prepared for this to take a lot of time. It's reckoned that with real-world projects of modest complexity that you can spend easily 80% of your time just doing data cleaning and data organisation. So the more work you put up front, the less you'll have to spend doing this data organisation. But sort of be prepared to spend time doing that. Don't storm straight on to doing stats. Right. One thing that I came across on Twitter just a day or two back, which is sort of related to this. This paper here is it's a retraction from German Medical Association, and what happened there was they were looking at sort of an intervention on sort of patients with COPD, and they analysed their data, wrote up their paper, and then sometime later realised that they had got a column in their data coded 1 and 2, and that was recording whether patients were assigned to the treatment group or the control group. And they realised that when they analysed the study, they'd got those swapped completely the wrong way round. So they sort of they analysed the data, found that the treatment was so successful, and that patients in one group were doing really well, and patients were doing really badly. They wrote it all up, did lots of diagrams and sort of tables, wrote a long discussion explaining why this was so. And then later they realised that these things were swapped around the other way. And so they had to retract the paper, which they did in a very nice way, and they were very humble about it and explained what had gone on. And they actually then republished it and then had to explain why the result was the other way around. I have also heard of that happened with someone very near to submitting their PhD, where they got codes 1 and 0 for diseased and healthy, and they swapped around the interpretation. And so they wrote their whole sort of thesis chapter explaining why all these things cause disease when actually they caused health. So that's something to be very, very careful about. And I think there was a time when statistics software required just number coding, and when sort of memory was expensive in computers, you would code diseased and healthy as 1 and 2, or male as 1, female as 2. I would suggest now that most software will let you, and so I would strongly recommend that you use text where you can. And if your stats software doesn't let you use text, I would change your stats software. Because with this, if rather than using 1 and 2, if these folks had used treatment and control, then the problem wouldn't have happened, because that would have been apparent throughout the analysis. But they just messed up this coding. So think really carefully when you start using cryptic codes in your data for coding. That was a bit of a rant, but I suspect that these authors of this kind of really wish they'd sort of thought about it back when they wrote the paper. So I probably won't apologise for the rant. Think carefully about coding your data. Okay. Right, so carrying on the workflow, you've designed your project, you've worked out how big it's going to be, you've collected your data, it's carefully organised, it's secure, it's resilient, you've been very good about your coding, so it's kind of clear what's going on, and you've got a data dictionary. What you need to now do is start looking at the data. And before you start generating p-values and sort of writing up your results, the next stage is exploratory analysis and visualization. And this is sort of super important. So thinking about exploring your data, an example that everyone teaching stats uses for this, says Francis Anscombe made up the set data, and if you look here, we've got 4 data sets, 1, 2, 3, 4, and they're just XY pairs. Okay, so they're just 4 sets of pairs of numbers. Okay, yeah. And if you, with this data, work out the mean of X in each group and the mean of Y in each group, and you look at the variance and you look at the correlation. Remember, correlation describes how well X and Y can vary together. And if we fit a straight line regression model to them, describing how Y varies with X, if you look here, we get pretty much we get the same answer for every set. If you go away with the calculator and work all these out, you'll find that in each of these data sets, you've got exactly the same mean X, mean of Y, relationship between the two, slopes and everything. Okay. So if you didn't do anything other than just these statistics, you would sort of conclude that the relationship between X and Y is the same in each of these data sets. Okay. However, if you've done the right thing and gone on to plot it, this is a plot of the 4 data sets. And what you'll see there is that each data set has got quite a different relationship between X and Y. In the first set, there's what we call a normal sort of linear relationship with some variation. In the second set, Y goes up as X increases, and it goes down. Here we've got a sort of a very tight slope with what's one strange value. And in the 4th set, we've got actually X is all 8, where it's about 19. So going back, if you didn't do a data exploration and plotting, you would sort of get all these identical results with each set, but actually sort of the interpretation should really be quite different because there's more complicated things going on. I mean, in this set here, sort of fitting a straight line makes no sense at all because this y goes up and then goes down. So the message there is to exploit data before you start generating numbers. And this would be, I guess, my approach to exploring data. You're going to probably, with a simple project, end up with a single spreadsheet which has got columns, and then each observation is a row. So there might be sort of each row might be a patient, and you might have a column describing their age, their gender, sort of glucose before and after treatment in 2 columns, things like that. So first thing to check are, have you got the data you expected? Just do some simple sort of tallying, make sure you've got them, as many kind of rows as you've got subjects or observations, and as many columns as data things you've measured, like glucose, blood pressure, whatever. Then work through doing some what I call univariable summaries. So sort of with categorical data like gender, you just tally it, and this sort of stuff, it might not go in. This for every variable might not go in the core of a project, but certainly it would go in an appendix, and certainly you want to have done it. If you recruited 100 patients, have you got sort of 30 caring male, 70 caring female, or whatever? Sort of, do some tallies and make sure things kind of are what you expect. Okay. With ordinal data, so like pain score, you can do sort of tables. You can also do sort of plots like this, where this is actually car data, but we've done a count of the number of cars in some sample of each manufacturer, so you can do that sort of box plot there. Bar chart there to just show all the data, just so you start to get a feel for what's going on. This sort of univariable exploration of data is a really good way of finding problems as well. Here's a histogram showing the count of individuals. This is cars again at different fuel efficiencies. If you do this and then found one that was 10,000, that would be suggestive that there was a data entry error. If you do a histogram of blood pressure and find that there's values between, say, systolic blood pressure, 100 to sort of 90 to 150, then you find a value of 500, then clearly sort of someone's missed out the digit, so you might go back to paper records, so you might need to mark that as kind of dubious data. Okay, so you can use this sort of exploration to clean data. If you don't do that exploration and checking of the data, you could end up with something like this, where there's where sort of this might be a genuine observation, or it might be sort of something arising from data entry. So you want to sort of go back and be checking and exploring that. With numerical data, we can do the sort of the standards summaries, the means, medians, minimums, maximums, and these sort of plots. Okay, so dig around and explore your data. Then the next stage is to do what I call bivariable exploration. So then we start plotting things against other things and tabulating things. So tabulating here, I've plotted gender against adult and child, and so it lets me start to have insights on what I've got. Check that against sort of other records from the study to make sure that I haven't sort of coded something incorrectly or whatever. I can start to see if there's any sort of unusual potential confounding biases there. If in this case we've got 50% of a third of the males are adult, and so that's actually and about a quarter of the females. So you can say there's a slight sort of difference in the proportions of adults and males and females. That might matter later on, so we can start to just get sort of an angle on what's going on with our data. With numerical variables that are sort of plotted against categories, we can do things like box and whisker plots. So here we can see there's 2 groups, and some value we measured is the median's higher for group A than group B, and we can get an idea of the spread. Or if we want to be, if we want more resolution and detail, we can do histograms. So we can see there that there's in group A there's sort of almost 2 sort of groups of some value, and group B there's just one sort of spread there. So digging around the data, exploring it, and you don't need to be brilliant with this. It's just just use your stats software, use Excel, sort of talk to a statistician, get some help with it, but just work through every kind of bit of data you kind of generated and just get some idea about what's going on. The time was half an hour, right? Cool. Finally, if we want to look at numerical data against numerical, we can do things like sort of scatter plots here. So this is comparing a bunch of cars' engine size against fuel efficiency, and we can start to see relationships there. This might in part steer our analysis as well, because looking at these relationships, numbers against numbers, might let us choose what type of statistics to use. More on that later. Okay. Right. So that's exploring and visualization and kind of cleaning. It's just looking at the data and seeing what's going on. Now into the fun stuff. Is this okay? Is someone, anyone sort of feel we're going too fast, too slow, or sort of is this okay? Everyone ecstatically happy? Right. These coming differently. So, statistical tests and models. So, I've got time. I'm just going to remind you about sampling variation, talk about why we need standard error and constant intervals, and how they communicate uncertainty. Talk a bit about stats tests, not specifically mentioning any, and how they use p-values, and then talk about sort of how you sort of choose stats tests. That's massive, so this is going to be sort of going to be brief, okay, right? So, sampling variation. So, this is the key. If we didn't have sampling variation, then sort of we wouldn't need. If people didn't differ in their sort of resting heart rate, and if drugs either cured people completely or not at all, I'd be out of a job. So variation is kind of what makes stats necessary. So let's just imagine this. We'll whiz through this, but let's imagine that we want to work out what the mean weight of the UK population is. We can't afford to measure everyone in the UK. There is a mean weight of everyone in the UK, but that's not something we can go out and measure practically. So what we do is take a random sample. And we know from theory that the mean of a random sample is a good way of estimating the population we sample it from. So let's take a random sample of 10 people, and we get a mean, and we'll sort of jot that down there. Let's imagine we did this over and over again. We're sort of, in a normal study, you only get to take the sample once, but in my fictitious world of lecturing to you, we get to do it lots and lots of times. So each time we take a random sample of 10 people in the UK, just because of random variation, we're going to get slightly different answers as the mean from our sample. Okay? You wouldn't expect the mean of 10 people from the UK randomly chosen to give the same answer every time. So we get lots of different answers. They're kind of, on average, they'll centre around the true population mean, but we get different answers each time we do it. If we did that lots, and I've simulated this here, that's what we get. We get a sort of spread of answers, okay? And I won't sort of go through the pain of doing it with you, but if we did that with much bigger samples, we'd also get different answers each time we did it. But with a bigger sample, the answers we get and the means of our samples will cluster closer together. The bigger a sample, the less likely the answer from it is to be distant from the true population value. So small samples give answers that vary a lot each time you do it. Big samples give smaller variation, okay? So what we need is a way, when we do our study, of communicating how well our study has pinned down the population answer. We need a way of reporting the sort of sampling uncertainty that comes from this, okay? And that's what we use standard error and constant intervals for. Standard error is a measure of expected spread if we were to do our study lots of times. Okay? And so standard error will be smaller with big studies, and it will be larger with small studies. It's a sort of, I guess it's a measure of certainty, okay? Even more so useful, I think, is a thing called a confidence interval. And with that, what we do is we give a range. So we run our study, we get 5 or whatever like that, and we give a range which we are 95% sure effectively contains the population value. Now, to do that, we use that software because we can't do our study lots and lots of times. We don't know what shape this will be. So we use stat software to estimate it. But the key thing is because an estimate from a sample from a population is not going to guarantee to give you the population answer. You have to have a way of estimating how certain you are, and these two things are the the ways that you report that. Right. So the other problem we've got, because of, I guess, random variation, is that if we want to compare sort of two groups, so say two groups treated with different drugs, and we want to compare heart rates in those two groups, because of random variation, our two groups, are quite likely to have different heart rates. But that might not be because of the drugs. It might just be because of randomness. If I measure the heart rate in 10 random people, measure the heart rate, the mean of those two groups is going to be different. But it's not because of anything different about the groups. So what we use is hypothesis tests that let us see if differences we see between groups, effects we see between groups, are likely to be because of something going on, or whether it's completely explainable by just random variation. And the way this works is by sort of disproving null hypotheses. Okay, so say we wanted to see if a drug gave a different blood pressure to so say drugs A and B, and if basically patients receiving those drugs have different systolic blood pressures. What we do is we're interested in seeing if there's a difference. So we then aim to disprove a null hypothesis. We try and falsify sort of a boring null hypothesis. So in my sort of A and B sort of drug blood pressure treatment study, the null hypothesis would be that the blood pressure is the same. So in this case, they before and after treatment. Sorry, not two groups, but we take some patients and we want to sort of see if the drug changes their blood pressure. So our null hypothesis is actually that their blood pressure is the same after treatment before. That's what we want to disprove. Okay, that's what we're interested in. So remember that it's quite likely that the mean of all these patients' blood pressure after treatment will be different to the mean of all their blood pressures before treatment because of random variation. So what we do is we gather data from the patients before and after giving the drug, and then we run a statistical test. And the statistical test will report back how likely it is that the difference the statistical test will report back how likely we would be to see that difference if the null's true. Sorry, just focus on that, okay? So a stats test basically tells you how likely an observed effect is if the null is true. And that's what p-value is. P-value is the probability of seeing a difference you saw or an effect you saw if the null hypothesis is true. And that's why we get excited about low p-values. So a low p-value means that the observed effect that you're sort of seeing would be very unlikely if the null is true. So a low p-value suggests that you should reject that null hypothesis and take that as evidence of something going on. But the way you remember this is that if the p-value is low, the null must go. If p is low, the null must go. And typically in science, in sort of simple tests, we would use 0.05 or 5% as the critical value. So what we're saying is, if we run a study and we our statistical test suggests that we'd only see the difference we got, or an even bigger difference, 5% of the time, if there wasn't an interesting effect, then we say, well, that's unlikely, so that's evidence of an interesting effect. The p-value thing is horrible and nasty to explain, so I can deal with questions on that on the boards and do chat if that's not clear. But the key thing is basically a null hypothesis, a boring thing you want to disprove, gather evidence, run a stats test, and if the p-value is low, it means that you would not see that effect. There's a low chance of seeing that effect if the null's true, so that's evidence of something going on. Right. There's just a collection of things from the past that have come up in terms of stats tests. So one thing is parametric versus non-parametric tests. Both of them require a null hypothesis, something you're aiming to disprove, and both generate p-values. Parametric tests assume there's an underlying distribution to your data. So they might assume that the numbers you're collecting are normally distributed. And so by doing that, they can kind of make, I guess, a more powerful job of testing to see if your null hypothesis is likely to be explaining things or not. Non-parametric tests don't assume an underlying distribution. So they are they're more robust. So if you haven't got normal data, if you've got sort of very skewed data, or if you're just measuring things on a sort of a pain scale rather than a genuine number, they will survive that, but they're probably less powerful. So that's parametric tests assume an underlying sort of distribution of data, and non-parametric tests don't. I don't know if that's useful or not, but that's the key sort of thing between these two tests. Non-parametric tests are pretty good, so often they will sort of do almost as good a job as these, and they will survive, say, sort of data which doesn't satisfy the assumptions and sort of needs of a parametric test. Right, multivariable models. So tend to just look at sort of one thing against another. So it might be sort of was blood pressure in the treated group different to blood pressure in the untreated group? Is there a difference in mean of blood pressures between these two groups? Okay. Multivariable models, which are a form of stats test, I guess, and quite often these are regression models, allow you to consider multiple influences. So as well as considering treatment group, yes or no on the outcome blood pressure, you can also factor in age and gender and baseline and things. And that's the power of these. They allow you to correct for other sort of other factors. It allows you to deal with the issue of confounding, where sort of there might be something else related to the treatment that's affecting the outcome. So you can kind of build more complex models, and they also allow you to make inferences on what's associated with an outcome. If we sort of have a multivariable model on, say, developing disease, we can include a number of different factors under the sort of the inputs, the predictors of that model, which then lets us try and understand which things are associated with disease whilst correcting for the other things. So that's where multivariable models come in. It's allowing kind of correction for other factors and identification of sort of multiple influences and dealing with confounding. Right. Thinking on regression models, and these are, I think, the main ones you'll see in kind of clinical papers. These are the different types of regression. And what I've done is explain sort of what the outcome is, what numbers you tend to get out with them, and how you interpret it. So I'll whiz through this, but I think these slides will be kept, so they're there. And there's many more as well. But linear regression is sort of, we know that from, that's fitting straight lines through things, I guess, and more complex versions if you use multiple regression. But if you have a numerical outcome, so if you have something like sort of heart rate, glucose level, sort of something like that, then we use linear regression to study numerical outcomes, and what we get out of that is we get coefficients which describe how that outcome changes per unit of something. So we can describe how glucose level changes per year of life, or we can sort of how blood pressure changes per dose of drug and things like that. So that's a linear regression. Suddenly, not everything in the world sits on a straight line. So then we've got things like non-linear regression, which is very similar, apart from it lets us describe things where might go up with increasing dose of drug and then might go down. So there might be a sort of a curvy type response. So that's non-linear regression. It's still predicting numerical things, but it allows more complex relationships. Very common in clinical life, clinical science, are things called logistic regression. And I've got some friends as well. There we're dealing with binary outcomes, yes/no outcomes. So did someone develop disease or not? Did they sort of go into remission or not? Did they die or survive? So if we have a yes/no outcome, then we use logistic regression. So we're no longer talking about numbers, we're talking about the simple yeses and nos, alive or dead, sort of discharged or sort of not discharged from hospital, whatever. And those models end up with odds ratios, which an odds ratio effectively describes how the odds of the interesting outcome, say surviving compared to dying, changes per unit of predictor. So for every year older, the odds of surviving might go down. The odds of surviving might sort of change if we're male versus female. So odds ratios describe difference in yes/no outcomes, and that's what we get from logistic regression models. Further on from those, we've got ordinal regression, which is where rather than yes/no, you've got ordered categories. So you might have no pain, some pain, extreme pain, so like a 3-level pain score. or clinical grading, or sort of tumour grading, or disease grading, or staging. Okay, and because that's not yes, no, but it's not really a number either, we can use a more complex regression with those. And again, they come up with odds ratios, and they describe the odds of being up a level in that sort of hierarchy of categories. That's definitely one to talk to statisticians about, because there's lots of tricky complexities to that. But just be aware, if you've got a sort of an ordered categorical outcome, there's a set of things that's designed to deal with that. And then the final one is also, it's complicated, and that's survival analysis, which is rather than just something happening or not, or something being a number, we've actually got the time to something happening. So sort of how long patients lived before they died once diagnosed. But this particularly matters when we've not got complete follow-up. So often with a study, we'll run a study, so we'll have patients and they're diagnosed, we might follow them for 6 months, and in that 6 months, they may die, or then at 6 months, we may lose them from the study. That's a complexity which can sort of bias and skew results. So that's the world of survival analysis, cost proportion hazard models, Kaplan-Meier plots. You've seen plenty of clinical papers that have these in, and there's a whole area of statistics to deal with that. It estimates hazard ratios, and a hazard ratio is a bit like an odds ratio, but this is the effect of, it's the difference between, say, groups or in response to a variable in terms of the chance of something happening per sort of units time. Okay? So sort of if males may have twice the hazard ratio of females, which means in a unit of time they are twice as likely to die or something happening to them. That's a super quick overview of the more common regression models. Don't worry, the end is in sight. There's only a couple more slides and then we can have questions. Okay. Choosing tests and sort of a stats test or model to use, it's going to be driven by your study design and your hypothesis. It may also be driven by your data, in that you might have great plans to use one type of statistical test, but then if your data don't seem to follow a distribution or are sort of skewed, or there's other complexities, you may need to then revise things. And that's the time to sort of take advice. You know, you've explored your data, you've done some plots and things. Down here we have that Anscombe set. So, linear regression would make sense for this, but here something weird is going on, so we might need to use a sort of a curvy model rather than a linear model to do non-linear regression. So their data might choose the sort of the way we analyse it. You need to consider sort of any assumptions we test. That comes back to your data, sort of making sure your data sort of fits with this model test assumptions, and this starts with making sure inferences are sensible. You can fit straight lines through anything. We could fit a straight line through the time people taken to, the fastest time for running a mile since the records were kept. But if we fit that straight line, then we might find in 200 years' time we're predicting someone would run a mile in no time at all, and that doesn't make sense. So sort of make sure that sort of what you're concluding from your sort of model sort of makes sense. Right. Okay, so last bit of the workflow is the write-up. I mentioned this on Monday, but I'd refer you there. Well, there's two resources. One, existing kind of well-written papers. So see how other people have written up this. So see what tables they use. Look at the different ways people have described their methods and portrayed their results and discussed them. And there's a real art to writing up methods that sort of is concise but sort of clear, and to make sure people can understand what you've done and have a chance of being able to reproduce it if they did a similar study. Definitely look at the reporting standards. So this is the one Stroke for observational studies, clinical trials, systematic reviews, diagnostic test evaluations. If you Google quartet network, myself and Marsh will be pointed at that, but there's a wealth of reporting standards on the web. They're being updated. I work in the veterinary field, so now we have a veterinary Stroke one. There's lots of these beautiful checklists of everything you should do in terms of writing up your method to explain what you've done, and then sort of how to kind of report it. And one final point of this is, when you write up, sort of make sure there's this sort of matching here, so that make sure that sort of when you describe the methods in your study, that then you write results that ostensibly have come from those methods, and anything in results should appear in the methods. So it's always troubling if someone says they're going to do 3 things in the methods, and then you only see 2 of those things in the results. You kind of wonder whether they forgot or just didn't like the 3rd thing. Likewise, if you see a graph in the results, but there's no talk of kind of where that data come from or how that was produced, or what if there's a p-value in the results with no mention of where that came from, then I kind of wonder sort of what's going on. So sort of, I think it happens more with multiple author kind of projects where sort of people write different bits, but just make sure there's a sensible sort of matching up between those bits. Right, that's it.